teaser talk for the PyPy training session. Okay. Disclaimer, we didn't really understand how the teaser talk worked before, like half an hour ago. And so we believe in JIT compiler, and so this is a just-in-time talk or something, and we prepared it now. So, what is PyPy? Well, PyPy is an open source project which started 8 years ago. And it's two things. It's a framework for developing fast dynamic languages, and it's a Python implementation which uses this framework to develop a fast Python interpreter. For most Python users, the latter is the most interesting thing, but the framework itself is also interesting if you want to develop your own language or if you want to make an existing language faster. So, since we are talking about speed, this is a graph which shows the performance of PyPy compared to CPython on a set of benchmarks which we collected around. Most of them come from the Onland and Swallow benchmark suite. Other, we took some existing Python program or library and we benchmarked it. As you can see, PyPy is faster for most things, sometimes even like 100 times faster or 10 times faster, depending on the benchmark. What is the training session about? PyPy is divided into two pieces, and the training session will be divided into parts. Part one is for people who are interested in using PyPy as an alternative Python interpreter. So it will show you how to run your application on PyPy, and what should work, what can go wrong, and how to use some tool that we developed to optimize a Python program for PyPy and to inspect what happens in the JIT. And part two will be about writing interpreters. So we will really try to start from a toy language, a very, very small toy language, and explain how to make it JIT friendly, and so you can make your language very fast. So now this will be a very quick overview of what will be in the training session. How to run PyPy? Well, it's a Python interpreter exactly as CPython. You can start it, it has the interactive prompt, and so you just use PyPy wherever you use Python and it should work. Apart tons of the code that you can go wrong and should not. For example, during the training session, we will give a challenge to the participants. There is this program which prints an HTML list of Fibonacci numbers. The implementation is deliberately complicated to introduce bugs that seem to work fine on CPython, but they don't on PyPy. And so you will try to run it on CPython, to run it on PyPy, and to fix it. Can we try to run HTML demo both on PyPy and CPython? Yes. So it's in the SRC. Okay, so this is the program, html-fibo.py. Try to run it on, but first on CPython maybe. It works. It prints an HTML list, very simple, yes. Then you run it on PyPy, and it doesn't print anything. So PyPy sucks, no. No, really. I mean, if you look at the implementation, you get scared. I mean, it's even scarier than the black magic thing that Armin, the other Armin, showed us if it doesn't work on PyPy, it's not because it's a bug in PyPy, it's a bug in your code, because it's relying on implementation details of CPython, in particular reference counting in this case.
Yes.
Yes, in this case. Sometimes your program doesn't work and it's a PyPy bug, but we are not advertising it. Let's go back to it. So yes, in the training you will try to understand what's wrong and to fix it, but not now, of course. So, now we will give a question.
Would it give the same behavior in Python?
Yes, probably. Probably Jython and EuroPython will exhibit the same behavior as PyPy, because they also don't have reference counting and they rely on non-deterministic GC. For the training session of tomorrow, we will go in the details of the just-in-time compiler. So for getting the best of it, it's good to have an overview to know what the JIT compiler is and how it works. So Armin will give briefly a presentation about it.
Okay, so more details tomorrow, basically. But what we have in PyPy is a tracing JIT compiler like TraceMonkey, and it is complete by construction because it's not written specifically as a JIT compiler for Python, but it's written as a JIT compiler for any language for which you write an interpreter in our Python. So we'll show in particular during the second half of the training tomorrow how you can write actually such an interpreter and get a just-in-time compiler for it for free, basically. And well, this just-in-time compiler supports Intel 32 and 64-bit platforms and ARM. I think the soon should be crossed by now. I mean, it really supports ARM. How does the JIT compiler works? Well, the basic idea is that when you start your program, you run it with the interpreter normally, and then when the JIT compiler notices that your interpreter is repeatedly interpreting the same function or the same loop in the function or something like that, then it will compile this part of your program into machine code. And how does it do it actually? It's a tracing JIT approach, which means that in order to know what the language interpreter wants to do on this particular loop in your program. So remember that our JIT compiler is general in the sense that it does not have knowledge about the detail of Python. So what it does is it asks the original interpreter to run in a special mode in which we do both interpretation and tracing, which means we record everything that the interpreter does. So we run in this mode for one iteration of the loop only, and then we get a list of operations that were done by the interpreter for running this particular loop in your program. And then from this list of operations, when we apply some optimizations, like GCC basically, but they are a bit different because trade-offs are a bit different simply. And then we get a trace of operations and we compile it to machine code, and then whenever your original program wants to run the loop, instead of using the interpreter, well, it just jumps to the machine code. It's a basic idea.
Okay. So, this was the general overview of how the JIT works, and we show it in a concrete example now. We will show how to run we run a very simple program in CPython, it's low. We run it on PyPy, it's fast. Well, yeah, yes, try. It's a count. Well, maybe we can show the source code. I don't know if it's in the slide. Yes, show it. Yes. No.
Sorry. Just a second. I need to resize my window.
Yes. Not the best font ever. But
Yes.
so this function is very simple. It counts how many numbers are multiple of 5 in a very stupid way, by the way. But we needed something simple, and well, then it tries to run it for the number you pass from the command line and type it. And we show that in Python it takes a lot. No, 10,000. No.
Okay.
Yes.
That's 10 million.
Yes, in CPy it takes 1.5 seconds, and now crossing the finger PyPy is faster. Yes, it is. And now the Python it's
What Python version I'm using here probably is the wrong one. Let's use Python 2.7.
Yeah, but well,
Okay.
between Python 2.5, 6, or 7, the performance of this kind of code doesn't change much. There is a question there.
They also have
Wait, there is the microphone coming.
We also have figures for comparing this to optimized C code.
Yes, probably. We don't have it at hand. But, well,
We
usually,
can try basically, but
Okay, I can try it and
yes.
we'll show you.
usually we are on the same order of magnitude for this kind of code. Well, I don't know maybe for this particular one.
The same order of magnitude might be 2 or 5 times lower than C code compared with other optimization.
well, you have a general idea. It's about that.
Yes, for this kind of code, yes, it's about that.
Yes, but there are two reasons for this. One is that GCC can spend more time optimizing because it's an offline task. And the other is that even if we took more time, we didn't develop most of the optimization that GCC does so far. So, but yes, in theory, we could provide a special version of PyPy for server, long-running servers that generates code as good as GCC.
Yes, for example, by generating C code and asking GCC to compile it or something.
Yes, so in this case, the PyPy did a good job and it worked fine. But if you want, for example, if you have a program that is not as fast as we expect, or we want to inspect what happens under the hood, we can use the tool that we developed for inspecting the JIT, the code generated by the JIT, by setting, for example, the PyPy log variable. Yes, for example, like this. With this syntax, it generates all the information about the JIT in the file named log, which contains a lot of things. In particular, the intermediate representation for the loop you saw above for counting the multiples of 5. Then we can start the JIT viewer, which is a nice web application for inspecting it. Yes, you can just visit
Alright, okay.
the Rigo viewer. Right? Can you maybe make it bigger?
Yes.
Yes, some people will make control minus.
Yes.
Right, okay. Then here it shows you all the loops that it compiled in this particular example. There is one, the other is implementation detail or something. You click on it, and here you see a nice view of the Python code. You see in Azure, what is the English name of this color? Yes, whatever. This color. And for each source code line, you see the Python bytecodes And for each bytecode, you see the low-level operation. These low-level operations are more or less the same level as C.
So in this case, it's assembler, basically.
Right.
It means that the code that we see in Vian has been compiled all the way down to these assembler instructions.
Yes, and if you inspect it, you can.
Science.
By inspecting the code, you can see how optimized it is. It's not completely because there is some useless code, for example, go up. You see there is a multiplication because it's the step of the range. And we didn't realize that the step is 1, and so we multiply by 1 because I12 is a variable, the value will be 1. But yes, in theory we could make our JIT better and optimize this special case. And what is that is simple. The greater or equal than operation at the beginning is the check for the loop if we are at the end of the range. Then we increment both the counter and what else?
The guard.
The guard.
Like describe
Right. Indeed. The guard is indeed the condition of the loop. We guard that I14 is false, which means that I9 is not greater or equal than I10, which means that basically we are still in the range of n. If the guard passes, which means if I14 is false, then the loop continues like this. If the guard fails, then we bail out of the compiled code and we go back to the interpretation in this case. This is the body of the loop. This is the modulo operation which checks that if the number is a multiple of 5 or not. Note that the modulo in this case has been optimized. No, it's not. It's really doing the int modulo operation. And then at the end we check again here if the result of the module is 0 or not, which means if the if above go up. Yes, this is the condition of the if. If it's equal to 0, do something, or else do something else. In this case, we are compiling the case for which the condition is true. So we increment this variable, and know that this variable is just a C-level or assembler level variable. I31, which is the counter, it can be kept in a register of the CPU. You don't need to allocate the int object and set the field and read the value again, and etc. At the end, there is a bit of bookkeeping for we do at the end of every loop to check if it's time to check for signals, like if you press Ctrl C or something. And there is already again a guard. Usually you don't check, so the guard will pass. And then we jump back to the loop and repeat again.
Yes, so you have to think about this operation as assembler operation. So that's why it's fast, basically.
The microphone.
The I37 for example is a register
No,
or a variable.
It's a variable. I mean, we have well, at this level they are variables. Then the CPU backend it has a register allocator and decides whether to keep the variable in a register or in the stack or.
Okay, thank you.
Yes, the I concretely means that it's an integer value. If you use those, you get an F, a pointer, you get a P. But the point is that they are machine level values. They are not boxed values for Python or whatever. I think that's for the GTU part. It will show better tomorrow, of course. And yes, we showed this. And before coming to the talk, if you are interested, as we all, we ask you to do a bit of preparation on your laptop. Well, you are encouraged to bring your laptop because we will like you to really do this stuff by yourself, not only watching us do it. There will be the challenge to solve, and in the second part we will give you some exercise to make the toy language faster and JIT-friendly. But to save a bit of time and be ready at the beginning, we ask you to prepare a bit and install something on your laptop. In particular, install PyPy if you didn't do. But also there is a checkout of the PyPy source code to do. And all the steps needed are available at this URL, which is just the URL on the schedule, the tag description on the schedule of the EuroPython website. You go there, you click there, and at the end there is the steps, or the how-to for getting prepared. So I hope I convinced you to come, and see you tomorrow.